Okay. Hello everyone. So today I'm going to discuss about the first chapter in this course, which is the uh, equilibrium combustion thermodynamics. So in this topic itself, you can see that we are talking about equilibrium processes. So okay, before proceeding into the analysis, we'll first state the assumptions involved in our further discussion. The first and important assumption is that the chemical reactions involved in this all the propulsion devices always occur between gases, and we can approximate all these gases to, per- to a perfect gas behavior, or which is an ideal gas behavior, you can say. Or I can say that PV is equal to rho RT, and CP and CV are functions of temperature. These two conditions are satisfied. This assumption is okay because fuel will evaporate first and then combustion occurs. Second assumption is that the chemical reactions are in equilibrium. This is okay for jet engines but not okay for rockets, because in rockets expansion will occur very rapidly, which cause unsteadiness. And due to this they are not in equilibrium. So next, some basic chemistry. We call reactions as exothermic if they release heat to the surroundings, and best example of exothermic reactions are combustion, that is this kind of reactions. Next, we define another quantity called as heat of formation. To be specific, you should call it as heat of formation at a specific temperature and pressure, which is the heat absorbed when 1 mole of the substance is formed at constant pressure and temperature from its elements in the natural state. Say, for example, say graphite carbon plus oxygen gives CO2. So the heat of formation, this QF, is defined for this reaction, or the QF of CO2 is characterized by this reaction, which is minus 393.522. Again, it's negative because it's an exothermic reaction, it's a combustion reaction. Whereas dissociation of oxygen is an endothermic reaction, which is opposite of exothermic, and hence QF is greater than 0. And again, since we are talking about equilibrium, only end states matter here. And then another assumption involved is a steady state process. So because this is in steady state, we can say that if no shaft work is present, the heat transfer is equal to the change in enthalpy. With obviously, if we ignore the changes in the kinetic and potential energies, so this Q is equal to delta H. Or I can write as heat of formation is equal to heat of products minus heat of reactants. Say I can write a general reaction which is occurring in three steps. First step, the reactants at T1 will be heated to temperature, say TF, where TF is the temperature at which the reaction occurs, and then some heat is provided so as that reaction occurs. So that reactant is converted to products at constant temperature, and then it comes back out at some temperature T2. So I call this as a heat exchanger, reaction chamber and heat exchanger, Q1, Q2, Q3. So I define some quantities called HRPF, which is the enthalpy change at constant reference temperature TF. And this reference temperature is usually room temperature, which is 25 degrees Celsius. Again, it varies. Some people have some different sign convention, some different temperature convection. Standard convection is 298 Kelvin. Next, we define quantity called as adiabatic temperature, which is the temperature of the products when combustion occurs adiabatically in absence of shaft work and neglecting changes in kinetic and potential energy. By this, I mean that the total heat Q1 plus Q2 plus Q3, this sum of these three heat should be equal to 0 because it's an adiabatic process. So, from this, I can say that since Q is equal to delta H. Q equal to 0 implies delta H is 0, which is enthalpy of reactants is equal to the enthalpy of products. So the enthalpy of products is nothing but the enthalpy at the adiabatic flame temperature. So I can write the above reaction and in the form of HT diagram like this, where this step 1 represents the enthalpy change at constant temperature of the reactants, and the step 2 denotes the enthalpy change at the reaction chamber, and step 3 is the enthalpy change at constant temperature of the products. Yeah, that's it for today. Thank you.